Okay, so we just got done talking about the concavity test. Now we got another test. It's the second derivative test. We also had a first derivative test, and along came with it was the increasing decreasing test. Okay, so they're very analogous to one another. The first derivative test allowed us to see if a critical number was a minimum or a maximum by testing the intervals around it to see if it was increasing or decreasing. Now, the second derivative test does something very similar. Okay, it allows us to find local minimums or maximums at our critical numbers by looking at the intervals around it and seeing whether they're positive or negative. Okay, so if you read the paper, it says suppose that C is a critical number of a continuous function f. Okay, so they're saying we need the critical numbers. That's telling us our first step in this process. We need to take the first derivative, set it equal to 0, and find those critical numbers. That was exactly the same first step as we did with the first derivative test. So that's what the if f prime of c equals 0 means. F prime of c equals 0, meaning we need to find the critical numbers. And f double prime of c is greater than 0. If you have these two conditions, this means that there is a local min at x equals c. Now let's go ahead and illustrate what this means. So, if you recall the definition of concave down, what being concave down means is on some interval, so just from A to B, on some interval, whatever that interval is, the tangent lines are below the graph. Okay, the graph lies above its tangent lines. Now we could see we have a local minimum at our value C right there. So this is just by definition of concave down, concave up right here, not concave down. Okay. By definition of being concave upward, all values on this interval, the second derivative should always be positive. Since C is inside this interval, the second derivative of that C value should be positive. So, if first find the critical numbers, then plug them into the second derivative and see whether they're positive or negative. If they're positive, you have a local min, and then if they're negative, you have a local maximum value. Okay? So now let's do an example. So we've already seen this example before. So the first thing we need to do is find the critical numbers. So that says take the derivative and then set the first derivative equal to 0. Alright, so we've already done this calculation, so what I'm going to do is I'm going to give you the factored form of it already. It was x minus 3 and x plus 1 is equal to 0. So we got x is equal to 3 here, x is equal to negative 1 there. So here are our critical numbers. X is equal to 3, x is equal to negative 1. Okay, not only that, to see whether we have minimums or maximums at those points using the second derivative test, we need the second derivative. Now, all we have to do, each one of these, we know f prime of 3 equals 0. We know f prime of negative 1 equals 0. So the first two conditions of the the first condition of the second derivative test is satisfied. Now we just need to evaluate each of these critical numbers. You get 6 times 3 is 18. 18 minus 6 is 12. This is greater than 0. Okay? So f double prime of 3 is greater than 0. When you have the critical number equaling 0 for the first derivative, and the second derivative, it's greater than 0, we have a local min. So this one's going to be less than 0. Let's go ahead and see why. F double prime of negative 1 is equal to 6 times negative 1 minus 6. Well, this is equal to negative 12, which is less than 0. 6 times negative 1 is negative 6. Negative 6 minus 6 more is negative 12. So we have a local max here. Put a line down there. There we go. And that's just the second derivative test. Okay? Now, let's go ahead and recall where we were concave up and concave down from doing that concavity test. Okay? If you recall, we had an inflection point at x equals 1. So it split our number line where we had 1 right here. And then we picked test values. Okay? We found over here that the interval was always negative. Okay? We found over here this interval was always positive. Now look at where these critical numbers are. 3. 3's over here. When it was positive, it was concave concave up. When it was negative, it's concave down. 3's in this interval from 1 to infinity. Everywhere is positive, so it makes sense why f double prime of 3 is positive. It's concave up as well, so it looks something like that. So we should expect a minimum at 3. We have some inflection point at 1, and then over here at negative 1, we have a maximum. This is c is equal to 3, this is c is equal to negative 1. Okay? So now, you've got the first derivative test to see whether or not a critical number is a local min or max. You've got the second derivative test to do the same exact thing, determine whether a critical number is a min or a max. It's up to you whether you pick one or the other to find the critical number or to determine that. However, sometimes the first derivative test is a lot easier to do because finding the second derivative may be difficult. In my personal opinion, I like doing the second derivative test because you're just evaluating points. You don't have to do test values, find where the intervals are positive, negative. In my opinion, that takes a lot of work. Okay? But if the second derivative is very messy, very complicated, then sometimes the first derivative test is beneficial because you only have to take one derivative. You will have to do a second derivative test on the Chapter 4 test. So you will definitely have a first derivative test question, and you will definitely have a second derivative test question. So you need to know how to do both.